Okay, hi everyone. I'm going to try to do it a little bit differently this week, just because there's a lot of formulas and matrices, and I made some calculation mistakes on Wednesday, so it's better if I just make sure that I have everything written. Any questions or comments that you want to bring up now? Silence? Want to remain silent? I put the notes in the Slack in case you want to follow along. Postpone deadline of assignment 3. You want to postpone the deadline of assignment 3? What day is it today? Is assignment 3 due today? When is it due? On Monday? But I mean, assignment 4 has to come out. I mean, we have to have assignment 4. If I postpone assignment 3, what's going to happen to assignment 4? Does Connie have an answer to my question? I can't, because the problem is that we need, how many? We need 5 or 6 assignments. I can't remember what I promised, but there's not enough time to postpone assignment 3. I mean, I didn't give term tests, right? So you're coming to me who didn't give you a term test, and you're asking me to change the syllabus, right? Think about it. It doesn't make sense, right? I'm not known as a soft one. Okay. Anyway, so okay, so let's do this. Let's go through the representations of SU2 and SO3. Okay, so try to focus on this very specific topic for today. Try to follow the argument. Try to follow the logic. Interrupt if you have a question. And I'm just going to review the setting, and we're going to get into this now. So. So we have 2 groups that we want to focus our attention on. We have SO3 and we have SU2. But SO3, these are the rotations. It's obviously, there's a mistake right away. So the determinant of R has to be equal to 1. Right? Because otherwise you would have the orthogonal group, you'd have the reflections would be included in there. So I've drawn a picture of SO3 as if it was a sphere, but it's not a sphere, not quite. And we have an identity element, which is a point on this space. And we have the tangent space to the identity, which is the Lie algebra of SO3. The Lie algebra of SO3 is, as we saw before, the set of 3x3 matrices, which are skew symmetric, and they've drawn them here. So you should think of such a matrix, okay, in case it wasn't already clear to you. This matrix, you should think of it as a vector, a tangent vector to SO3 at the identity element. So this is a velocity vector at the identity element. that if you were to go in that direction, what you would be doing is you'd be rotating about some axis. And there are three basis elements for this space of matrices, sigma 1, sigma 2, and sigma 3, which are infinitesimal rotations about x, y, and z axis. So here I've drawn it here. Here's sigma 1. Here's the x-axis. And what this thing is doing, if I exponentiate sigma 1, it's giving me a cosine cos submatrix, which is rotating in the yz plane by a certain angle t radians. Okay. And if we compute the Lie bracket between sigma 1 and sigma 2, right, you can check what's going to happen when you multiply one way. You're going to pick up a 1, right, in this entry. And when you go the other way, you're going to pick up a product of 1 where this entry multiplies this one, but the commutator is AB minus BA, so there's a -1. So the commutator of sigma 1 and sigma 2 gives sigma 3. That's what this commutation relation says. And then there's a rotational symmetry where you could just rotate x, y, and z, and we get the same expressions. It's just with 1, 2, and 3 cyclically permuted. Okay, so this gives us a well-defined Lie bracket on the vector space generated by these three elements. It defines a Lie bracket on R3. And you may recognize this. This is exactly the vector cross product. So this is the same as the vector cross product on R3. So the vector cross product is itself, this is a Lie algebra. The vector cross product mates R3 into a Lie algebra, and that Lie algebra is the same as the Lie algebra of SO3. So you can see that the cross product is intimately related to SO3, and that's not so surprising. Okay, now on the other hand, we have SU2. A matrix in SU2 looks like this: alpha, beta, and then the conjugates of beta and alpha are in the second column. This comes from the fact that U transpose bar is equal to the identity. And the determinant has got to be 1 if you want it to be an SU2. So when we require that the determinant is equal to 1, we get that the norm squared of this complex number plus the norm squared of this complex number is equal to 1. And if we write this out in terms of the real and imaginary parts, x0, x1 are the imaginary and real parts of alpha, and x2, x3 are the real and imaginary parts of beta. If we write this equation out, this determinant 1 equation, we get this equation, which is basically saying that these 4 real numbers are lying on the unit sphere inside 4-dimensional space. So you could say that SU2 is another name for the 3-dimensional sphere inside 4-dimensional space. That's just what it looks like as a set. It looks like a 3-dimensional sphere. So that's maybe this is a good picture of SU2. It's like a 3-dimensional sphere, not a 2-dimensional sphere, but a 3-dimensional sphere, which I can't really draw. And the tangent space to it at the identity element is a 3-dimensional vector space, which is R3, and the vector, yeah. And then if we go look at this, so now we can figure out the Lie algebra of SU2. It consists of those 2x2 complex matrices, which are skew adjoint with trace 0. And we counted this last time, that there are exactly 3 real dimensions to this space. And we saw that it's the same as the Lie algebra of SO3. Now, I had some factors missing, which are very important. If anyone actually tried to take the commutator of the first and second first and second Pauli matrix, you would not have gotten sigma 3. So it's not true that sigma 1 bracket sigma 2 is sigma 3. I made a mistake. You first of all need to take the self-adjoint Pauli matrices and multiply by minus I. That will make them into skew adjoint and make them into a Lie algebra under commutator. The second thing you need to do is divide by 2. And you don't have to divide by 2 to get a basis, but I want my basis to line up with the basis that I chose for SO3. So I need to need to multiply by 1/2. So these modified Pauli matrices, I will call x1, x2, and x3. Okay, and this will be a basis for my real three-dimensional space. And this one does satisfy the commutation relation x1 bracket x2 is equal to x3. And you have the other cyclic permutations of this. So just by taking a look at this, we just notice that it is the same Lie algebra as the Lie algebra of SO3. And to see that, we just send sigma I to xi, and they are in, and that's a good way of matching the two vector spaces up in such a way that the Lie brackets match up. Okay. Any question about this fact that we have two groups? They're both three-dimensional. They have three-dimensional tangent space at the identity. They have bases which we can identify with each other, and they have the same Lie bracket. It's just that one of them is described in terms of 2x2 complex matrices, that's SU2, and the other is described in terms of 3x3 real matrices. Any questions about this? That should be clear. It should be also clear from your reading in the textbook. Okay, so how do we see this? So here what I did was I just presented you one group, presented another group, looked at their tangent spaces, and then just computed and picked a basis that allows us to identify. That's not very natural. We would like to have a natural reason why these two are the same. So for this, we need to talk about the adjoint action, which I already started to explain. Any Lie group has a natural action or representation on its Lie algebra. Okay, so that means that every Lie group, it has a tangent space at the identity. That's a Lie algebra. And this group actually has a representation on that tangent space. And how does that representation look? Well, you just conjugate. So you take an element of the group, you take an element of the Lie algebra, and you conjugate like this. This is a definition that only works for matrix groups, but the textbook will have a general definition. But it's okay. This is quite good enough for us for now. And the point is that if x is let's see, which I'm in SU2, right? So if x is skew adjoint and U is an SU2 matrix, right? Then I want to check that the commutator, excuse me, I want to check that the conjugation of x by U is also skew adjoint. So I just made that little computation here, and you can just easily check that because x is skew adjoint and because U is unitary, this is also skew adjoint. So, and notice also that this is a linear map, right? If I take a sum of matrices x1 plus x2, that will go in here, and it will decompose as a sum. So this expression is not linear in U, but that's not what's important. The thing that's in a linear space is x. X is in the Lie algebra. That's a vector space. U is not in a vector space. It's in the Lie group, which is a curved space. Nevertheless, the action of U on x is linear. If I multiply x by 3, then this will be multiplied by 3. Okay, and then you can also, obviously, you could see that this is a representation. So if I take the product of two unitaries and I conjugate, then I can re-bracket, and I can see that it is the product of the two actions. And so this is our representation definition. So we have a representation pi from SU2 to the linear operators on this vector space. Okay, so we've defined a representation. This is a representation of SU2 on a three-dimensional real vector space. Okay, notice that this is very different from the usual representation of SU2. Normally, SU2 is 2x2 matrices and with complex coefficients. So it acts on C2. The matrix just multiplies against a column vector. Okay, so this is now the second representation that we have from SU2. We had one which is what's called the standard representation, where it just acts on C2, and now we have a representation on R3. Okay, so just summarizing, SU2 has a three-dimensional representation, the adjoint representation on its own Lie algebra. Okay, and let's take a look. Let's take a look at the properties of that representation. So there's something interesting about it. So a general element in SU2, I can take a sum of the basis, a linear combination of the basis. It's minus I over 2 times. Here I've written it in terms of the Pauli matrices. So you have AA, that's A times the first Pauli matrix. IB minus IB, that's B times the second. And C minus C, that's C times the third. And the whole thing is multiplied by minus I over 2. So we have a general element, and if I take the determinant of this element, this is just an observation. If I take the determinant, what I get is minus C squared, and then minus this multiplied by this, and that is just a complex number times its complex conjugate, which is just the norm squared. So that means what I get is going to be minus a quarter coming from this, times the negative norm squared of a squared plus b squared plus c squared. So you see that bizarrely, very strangely, the determinant of one of these elements of SU2 is actually the three-dimensional norm that we know in R3. So this is a strange thing. We don't usually think of the norm of a vector in R3 as being the determinant of a matrix, but indeed it is. And the cool thing is that if you take the determinant of UX U inverse, then you get determinant U, determinant X, determinant U inverse, and the determinants of U cancel out. So this means that when you conjugate by your element of SU2, you're not changing the norm, and therefore it's an orthogonal transformation. Okay, so this weird argument, which uses the determinant, is a way of showing that the way that SU2 acts as linear transformations here, it actually preserves a norm on this three-dimensional real vector space. And that means that this matrix, pi of u, one of these matrices, they are all orthogonal transformations. Okay, so this means that when we take u and send it to the adjoint action, which is just conjugation by u, what we're really doing is defining a homomorphism of groups from SU2 to SO3. Okay, so this is maybe one of the most natural ways of seeing the relationship between SU2 and SO3, namely that any SU2 matrix acts on its own tangent space, the tangent space of the group SU2, and the way that it acts on that vector space is that it preserves the norm. Yes, an element of SO3. So this operator, this is a linear operator that preserves the norm on R3 because it preserves the determinant on SU2, little su2, and that is the norm. So this means that we get a transformation which is in SO3. Okay, so the representation is actually giving us a group homomorphism from SU2 to SO3. Okay, so you may ask, what's the properties of this group homomorphism? So first of all, it is surjective. Okay, why is it surjective? Well, any rotation can be thought of as being a rotation by t angle around some axis. Okay, so for example, let's take as an example the z-axis. So a rotation about the z-axis is exactly an exponentiation of sigma 3. Sigma 3 is rotation about, infinitesimal rotation about the z-axis. If you exponentiate it, you get a rotation by t radians. and we get this matrix. So what we're looking for to prove surjectivity is we're trying to find a unitary matrix that when you conjugate by it will give exactly this for the adjoint action. Okay, and well, one way to do this is instead of trying to figure out this element u, which is going to be sent to this element r, what I could do is try to find something in the Lie algebra that's sent to sigma 3, so that when I exponentiate that thing inside SU2, I'm going to get the right thing. So so we know how to do that. We use x1. Remember, x1 is this matrix. It's minus I over 2 times sigma 1. Okay, and this one, if I exponentiate this e to the t x1, I'm going to get a path in SU2. And if I look at the value of this path, what I'm going to do now is I'm going to try to let this act on the tangent space to try to obtain this rotation. So let's see how that works. So if I take this element, so remember, this is an element of SU2 group, and we're going to try to see how the adjoint action acts on a general element in SU2 Lie algebra. Okay, and this is how it acts by conjugation. Okay, and now what we can do is take the derivative of this. So we could try to see, okay, this is going to give me a path. Yeah, so if I so basically, if this is just kind of demonstrating something that we discussed before, that this adjoint action is related to the little adjoint action when we differentiate. So I'm just working that out. So we have the big adjoint action by a path of unitary matrices. If I differentiate it in a specific direction, if I differentiate it with respect to t, we're going to get, if we differentiate this, you're going to get one term from the first factor that includes t and another term with the second. We did this calculation, x1x minus xx1. So it's actually the little adjoint action, the commutator against x1. So the infinitesimal way in which this acts is by commutator of x1 with the given matrix. And so here I'm just looking at what this does. What does this commutator do to the basis elements? So when I use this rotation in the x1 direction, how does it affect x1? Well, I just have to bracket it with x1 and I get 0. But x2, I get this bracket of x1 and x2, and it is x3. And x3 is turned to minus x2. So we see now how this transformation acts on the basis. I'm now computing the action of x1 on the basis for SU2, just by conjugation. And what you see is that the first basis element is sent to 0. The second is sent to the third basis element. And the third is sent to -1 times the second basis element. So this means that the matrix of this transformation on the Lie algebra is exactly the matrix that we used in SO3, which we called sigma 1. So in other words, this thing is acting on a basis of SU2. Oh, sorry, I was just computing the case for x2. So if we started rotating about the y-axis, or if we used, if we used e to the t x2, and if we acted upon little SU2 and saw how that transformation acted on the tangent space of the group, we would see that x1 is sent to minus x3, x3 to x1, and x2 to 0. So basically, we can see how these matrices are sent to these. So again, so this calculation, what is it doing? It's saying that we have a map tau from this group to this group. Okay, this tau, what it does is it takes a unitary matrix and conjugates, sends it to the conjugation operator. Now, if I took the unit inside SU2, the identity matrix, right, it would be sent to add of the identity, and that's just it's conjugation by the identity matrix, and that does nothing. That's the identity matrix. So that means that the identity is taken to the identity. Okay, and so this computation, what it's doing is it's computing the derivative of this map at the identity. The derivative is going to take the derivative of this map will take the tangent space, so the derivative of tau, if I evaluate it at the identity matrix, it will be a map from the tangent space, which we called little SU2, to the tangent space to the identity, which we called little SO3. Okay, and this is what I'm computing down here. I'm differentiating this conjugation with respect to t. Okay, and what we see is that this derivative takes the basis that we talked about to the basis that we talked about. So identifying these bases is not some arbitrary process. It's exactly the derivative of the natural map from SU2 to SO3. That natural map coming from the fact that every unitary matrix acts on its tangent space by conjugation. Okay, so yeah. So we get an isomorphism in this way because we see the basis being sent to the basis. Now, the warning here is that just because the derivative of the map is an isomorphism, it doesn't mean that the map is an isomorphism. For example, there's this famous 2-to-1 cover of the circle over the circle. So here I have a circle. I'm just drawing it in a curled up way. And we can map this circle down to the circle by just taking projection, vertical projection. Another way of writing it is that e to the I theta is going to be sent to e to the I2 theta. So if you go around halfway, like from this blue point to this green point, the blue point will be sent to a point down here, and the green point will be sent exactly to the same point. So obviously the derivative is just taking a tangent space to a tangent space, and that's an isomorphism. But the full map is not an isomorphism. It's not injective. It's surjective, but it's not injective. Okay, and pi rotation and zero rotation are both being sent to the same point. Oops, what did I do? E to the I0. Oh yeah, so 1 and -1 on this circle are being both sent to 1 on this circle. Okay, so so it's a clear, this is basically the prototype of what's happening between the two groups. So let's do the same, let's give the same kind of warning or the same behavior. Let's explore the same behavior for SU2. So tau is surjective. We just established that. Wait, didn't I just explain this? Yeah, tau is surjective. So, oh, I'm sorry. So I started it, but I didn't actually this. Let me get rid of this part. Oops. Okay, so to show that it's surjective, we use the fact that any rotation can be written as the exponentiation of some axis. Basically, this is saying that every rotation is a rotation about an axis. And what we're looking for is a particular unitary element that has this as its conjugation operator. And so what we do is we just take e to the t x3, the same element in the Lie algebra corresponding to the one that we're trying to cover. So let's do that. So we took x3. Remember, x3 was -i/2 times the 1 - 1 operator. And we exponentiate this. So what we find is we get this diagonal operator where we're just exponentiating e to the it over 2, e to the minus and plus I over t, it over 2. So this is a unitary matrix that depends on time. And this will indeed be sent to the this will indeed be sent to the same matrix. But the problem is this. So if we apply e to the 2 pi, if we take time to be 2 pi, okay, then it's clear that for 2 pi rotations in 3-dimensional space, this thing is just going to give the identity matrix. Of course, if you rotate by 2 pi about any axis, we're just going to get the identity. On the other hand, here, if I exponentiate this by 2 pi, then because of this 1/2, right, I'm going to get -1 here. It'll be e to the I pi or e to the minus I pi, both of which give -1. So we get minus the identity. So it's exactly the same thing that's happening in this case, right? So just imagine that you start here or start here, right? And you choose a tangent vector, which is the same, which is sent by the derivative of this map, right? This tangent vector and this tangent vector are the same. They're sent one to the other. But if you then exponentiate that, that means that you're going to start rotating around the circle. But of course, for the one on top, you're going to have twice as far to go. That's what's happening. So although the derivative sends this vector to this vector, it will take 2 pi amount of time for this vector to go around, but it will take 4 pi to get around here. That's the basic phenomenon. So there's an identification. Sorry, where is it? Yeah, there is an identification here. This is an isomorphism between the tangent space and the tangent space of the two groups. But this one only has to go around 2 pi in order to come back to itself, whereas this one has to go 4 pi. Okay, and that's demonstrated by this property. So we see that tau sends this element, which is not the identity, to the identity. So I've described this, this is the standard way that mathematicians use to describe these mappings of groups. We have a group homomorphism, and this mapping to 1 is just a way of saying that this map is surjective. This just means that this map here is surjective. And this here means that this map is injective. And the implicit claim is that the image of this map is equal to the kernel of this map. So whenever you write, this is called an exact sequence. It's called a short exact sequence. And the reason it's called an exact sequence is because the maps are they're not forgetting anything. They're like just, everything is very tight. So what it means is that if you look at this map from this group to this group, this 1 just denotes the trivial group. So there's obviously a map from this group to the trivial group. And what is the kernel of that map? The kernel is just the whole group. Okay, and the kernel of this map should be equal exactly to the image of this map, so that everything lines up perfectly, exactly. Okay, so the kernel of this map is the entire group. Therefore, the image of this map must be the entire group. Therefore, this map is surjective. Similarly here, the kernel of this map is the image of this map. That means, but the image of this map is just 1. So that is implicitly saying that the kernel of this map is trivial. And therefore, this is an injection. So exactness at this position is the relationship that the kernel of this map and the image of this map agree. to say that the kernel of this map and the image of this map agree is basically saying that you're not losing any information, that anything in here, roughly speaking, is either going to be sent here or is either going to be in the image of here, and you're not losing anything. You're exactly describing the group. So such a sequence, this just means that the kernel of fi is equal to the image of fi minus 1. That's all that exactness means. Anyway, so this is giving you a feeling for what the difference between the groups is. The difference is that there's a 2-to-1 cover from SU2 to SO3, and here's the kernel group. The kernel group is the plus identity matrix and the negative identity matrix, as we described here. This matrix, if we conjugate by it, we get the identity matrix on the Lie algebra. Okay, and just to kind of give you a little bit more visual or kind of intuition about this group, actually remember that the SU2 is the 3-sphere inside R4. So we have this picture of it as a 3-dimensional sphere, and we have this kernel here, which basically is saying that any matrix in SU2 is going to be sent to some matrix in SO3. But if I take that matrix and multiply by -1, it will be sent to the same point. So there's an action on SU2 by multiplication by -1, and that action turns out on the sphere. If you check it out in coordinates, if you write these, if you write it this way, and you multiply by the -1 matrix, then look what happens. C gets sent to -C, A gets sent to -A, B gets sent to -B. So A, B, and C, if you multiply this matrix by -1, they're all going to be sent to their negatives. And as a result, on the 3-sphere, what this thing is the antipodal map. It takes x, y, z to -x, -y, -z. Okay, so when you mod out, when you quotient SU2 by this Z2 subgroup, what you're really doing is taking the 3-sphere and quotienting it out by antipodal involution. And the antipodal means that you go from here to Australia. And when you mod that out, okay, you get SO3. So what the claim is that SO3 is almost the 3-sphere. It's just that you have to identify antipodal points. And you might learn at some point in one of your topology classes that when you take S3 and you mod out by antipodal involution, you get a space which has a name. It's called RP3, the 3-dimensional real projective space. So it turns out that SO3 is a group. As a group, it's better to call it SO3. As a space, it's better to call it RP3, because then topologists will know what you're talking about. Okay, that's the kind of setting that we're in. I just wanted to make crystal clear the relationship between the groups. So now I need at least 2 questions.
Is this the hop vibration, or is it completely different?
This is not related to the hop vibration. No. Yeah, the hop vibration is a vibration of the 3-sphere over the 2-sphere. It's not. We could discuss that, but maybe in office hours. How about that?
So we're taking the tangent spaces of SU2 and SO3, and we're finding a representation between them. And then...
Well, be careful. We're finding a map between them.
Okay.
We're identifying them. The tangent spaces, they're each 3-dimensional, and we're mapping one to the other. And that's, in a basis, it's easy to say how it works. It just looks like this. So there's 2 things that you need to realize. Okay, so there's an important, let's see, where are we? Yeah, this is the first important thing, that there is a natural homomorphism of groups from SU2 to SO3. Okay, and this is how the homomorphism is described. Every matrix in SU2 has a conjugation operator, big add of U. And what does this act on? You tell me. What does add U act on? This is an operator. It's a linear operator on a vector space. The question is, which vector space does this act on?
On SO3?
No. For every group, every Lie group has a Lie algebra, which is the tangent space to the identity element of G. This is a group. This is a vector space. Okay. And it turns out that every group element, okay, determines an operator which is called add G, add little g, sorry. Every group element H defines a linear operator, add H, which acts on this vector space. Okay, so every group element defines a linear map, a linear operator on a vector space, and that vector space is its own tangent space.
Mm-hmm.
Okay, it's and the point is that this is a representation. So if you take the product of two group elements, you'll get the product of the two operators. That's what I'm describing here. Okay, it turns out that the tangent space of this group here, the tangent space is three-dimensional space. And so when that group element acts on that tangent space, it's actually acting on a three-dimensional space. And so it's a rotation.
Mm-hmm.
Okay, so then I took the derivative of this map. So I'm trying to study this map. I want to know, is this map like an identification between these two groups? Are these two groups actually the same? Even though one looks like 2 by 2 matrices, the other one is 3 by 3. It doesn't matter. It could be that they're the same group. It could be that they're isomorphic. Okay, so I took the derivative of the map. And this derivative is a map now from the three-dimensional Lie algebra to this three-dimensional Lie algebra. And you can check that it's an isomorphism. It takes, if you take xi, the basis of the first vector space, basis of the second vector space, it takes one to the other. Okay, so we have a situation like this, which identifies tangent spaces, even though the spaces are not identified.
Mm-hmm.
Okay, that's what's going on. So this is one space, this is another. There's a map tau, homomorphism from this to this. But that homomorphism is not an isomorphism because it's not injective. There's a very small kernel.
Mm-hmm.
Okay. Sorry, I just went over it, but I feel like repeating it might be helpful.
Mm-hmm.
Any other questions?
I have a question.
Yeah.
So in the context of quantum mechanics, why would we want to identify these two spaces? Because you lose
Which two spaces? Which two spaces?
SO3 and the RP3. Because you kind of lose the algebra.
I am just, first of all, it's a group, not an algebra. Second of all, I'm just trying to give you, like I said, some topological intuition for what this group looks like.
I see.
SO3 is a space of group elements, okay, and you can think of them as rotations about an axis. And the interesting thing is that this is the same as the three-dimensional projective space, which was invented in Italy in the 16th century. Yes? They didn't know at that time that they were describing three-dimensional rotations.
Everything made in Italy is nice.
I doubt that. You may not be aware of some of the output of Italy, such as Sergio Berlusconi. Not everything is nice. So okay, so now let's do representation theory of SU2. We talked about U1. U1 is the master. If you know how the representations of U1 work, you're going to know how the rest of the representations work. So we saw that all U1 is abelian. All of its irreducible representations are one-dimensional, and they're labeled by an integer. This is called the weight or charge, depending on whether you're in math or physics. the charge K representation takes e to the I theta to a 1-by-1 matrix with entry e to the I k theta, where k is an integer. This is a linear operator depending on theta. It has the representation property and it's acting on a one-dimensional vector space. Okay, so how are we going to use this in order to study the representations of SU2? Well, we're going to look inside SU2 and we're going to find hidden in there a U1. So if SU2 is acting on a vector space, we're going to see that inside this SU2, there's a tiny little U1, and we're going to let the representation, we're going to try to see how does that little U1 act on the representation and what charge does it have? And that's going to give us some clues as to what representation of SU2 we're dealing with. Okay, so it's like, yeah. Inside every group, you've got a little U1, sometimes more than one of them. You always have some U1s inside a group, just like, they're like the little truck driver. This huge group is moving around, acting on things. But if you ask the person in control, it's really a little tiny U1 sitting in there, a little circle. So inside SU2, we have a copy of U1, several of them. And how can we see this? Well, one way to do it is to pick an element in the Lie algebra. I'm picking my favorite one, which is sigma 3. I multiply it by I multiplied by I theta to make it skew adjoint, and then I exponentiate it, and here you go. This is a U1 subgroup of matrices which are diagonal. They have opposite eigenvalue because, remember, this is in SU2, so it should have determinant 1. So by putting e to the I theta in this entry and e to the minus I theta, we get, obviously, a U1 subgroup of SU2, right? This is a subgroup of SU2. When I let theta vary, theta could be any real number. So theta can be from 0 to 2 pi. So we have a U1 subgroup. Is it clear to everyone that we have a U1 subgroup? I could have picked, instead of sigma 3, I could have picked sigma 2 or sigma 1. I would get a bunch of different subgroups. Or you could take any linear combination of the sigmas, as long as it had unit norm, right? Then after 2 pi theta, after 2 pi, theta equal 2 pi, it would come back to itself, just like here. Okay, I'm just putting it in diagonal form to make it obvious that we have this nice U1 subgroup. Okay, so this means that that we get a two-dimensional representation of U1 because now this is a 2-by-2 matrix. It's acting on C2, right? So when I write this matrix, what I'm really doing is I'm giving a two-dimensional representation of U1. Okay, and it's not irreducible. It reduces into a direct sum of two one-dimensional representations. Okay, so I've written that here. So this is a linear operator on C2 for every angle on the theta, every angle on the circle, every angle from 0 to 2 pi. I get a matrix, 2-by-2 complex matrix. So it is a representation of the circle. Okay, so how could I describe this representation? Well, how do you describe any representation of the circle? You give its weight. So if I wanted to describe to you this representation, and if let's say you were not a fan of matrices, I would tell you, oh, well, this is a two-dimensional representation of a U1, and it decomposes as a sum of two one-dimensional representations. One of them has weight -1, and the other has weight +1. And if I just give you that list of weights, that's all you need to know. And you know exactly which representation of the circle it is. And so here, this part has weight 1 times I theta, so the weight is 1, and this part has weight -1. So in the spectrum, I'm going to write the weights in red. So I draw a red dot because this representation has a one-dimensional part which has weight 1, and it has another one-dimensional part which has weight 1. So if you just look at this, Okay, this will tell you which representation of the circle we're dealing with. Is that clear? That this diagram basically tells you everything you need to know about that representation of U1. Okay. Any question about this?
I do
So
have a question.
This is identifying the weights of this representation, the representation which is 2 by 2 matrices. Question?
I want to ask, what's the domain of pi?
Can you say it a bit louder?
Yeah, I think pi is a composition, right? From U1 to SU2, and then from SU2 to the
Pi
yeah, pi.
of e to the I theta. Okay.
Yeah.
This is in, it's in a unitary group, right? It's a unitary representation.
No, my question is pi
I know,
itself.
just stick with me. So we're talking about an n-dimensional representation. That means that for every theta, this is a unitary matrix, right?
Yeah.
So in this case, it happens to be U2. This is a 2-dimensional representation. It's a 2 by 2 unitary matrix. This is acting on C2, C plus C. So I'm telling you what the 2 by 2 unitary matrix is corresponding to theta. This representation is a 1 by 1 matrix that depends on theta. That's an irreducible representation. This one is a reducible representation. It reduces into a sum of 2 representations.
Okay, so that matrix didn't exactly come from sigma 3.
Yeah, sorry, you're too quiet. I can't hear.
Okay, so that matrix didn't exactly come from sigma 3, correct?
So when we talk about, so both are true. What I said is true and what you said is true as well. The reason is because when we talk about these groups, whenever we give, when we describe SU2 as a matrix group, okay, what we're doing is we're automatically providing a representation because this matrix acts on C plus C. Okay, so some people, they don't like to think of groups as matrix groups. They like to think of them as abstract entities, right? So if you say, give me an element of SU2, they will say, well, in which representation do you want me to provide? Do you want a 2 by 2 matrix? Do you want a 3 by 3 matrix? What do you want, right? SU2 is not necessarily matrices. They think of it as an abstract space. And this is a particular 2-dimensional representation of SU2. It's called the standard representation, the representation that everyone knows because that's how SU2 is defined. Does that make sense? And the same thing goes for SO3. It's given to you as a 3-dimensional representation. Okay. The point is that not all representations have to be injective, right? There's my favorite representation of SO3 is that it acts on a 1-dimensional space by this matrix. Every single rotation of 3-dimensional space is represented by the unit 1 by 1 matrix. This is called the trivial representation. So you know, it would not have been very useful to define SO3 in terms of this representation because it contains no information. Luckily, when they told you about SO3, they provided you the group as a 3 by 3 as a 3 by 3 matrix, a 3-dimensional representation, which happens to be injective. So, you know, typically you could say that it's even in U3, right? This is the standard representation, which takes an SO3 element and just tells you which 3 by 3 matrix is it. Okay, so hopefully that helps. Does that address the confusing point? Okay.
Can I ask a quick question?
Yeah, go ahead.
If we were to choose a different sigma and the e's were in the off diagonal, could we still express that as the same sum?
Yes, we would have to diagonalize it. All of those, If you take any one of those, we're going to get a unitary matrix. And those are always diagonalizable. Or even if you take the Hermitian matrix, right? Sigma 3, sigma 2, sigma 1, they're all Hermitian. They're all self-adjoint. All of those are diagonalizable. So you can always diagonalize it, and it will always look like this, because they have to have inverse eigenvalues since their determinant is 1. So this is completely general. It's true for any self-adjoint matrix like this. Okay, so just keep in mind this way that we drew this picture. That's important. We drew this picture because we have a one-dimensional piece of weight 1 and a one-dimensional piece of weight -1, and we can see that the representation is being decomposed. It's almost like the two-dimensional vector space. You should think of it like this, that you have this two-dimensional vector space, C2, and then we're decomposing it as a one-dimensional space over this point and a one-dimensional space over that point. And we've kind of split the space into two one-dimensional spaces. Okay, so what did I write here? We have taken the standard representation C2 and expressed it in terms of irreducible representations of a little tiny U1 subgroup inside, okay? Now, okay, so what I'm saying here is a warning that C2, it is decomposable as U1 representation for this obvious reason. It is decomposable into one-dimensional representations. However, it is irreducible as a representation of SU2. Okay, if I take a non-zero vector, did I prove it here? So if I take a non-zero vector in C2, right? If I take a non-zero vector in C2, and if I act on it by all matrices in SU2, it's going to get moved around in all possible subspaces. Okay, you will never find a vector which will be sent to a one-dimensional space, right? If C2 was if C2 was decomposable into two one-dimensional pieces, then that would mean that all matrices in SU2 can be diagonalized simultaneously. And there's no way that's true because they don't commute. Okay, so it is irreducible, and the reason it's irreducible is because the matrices in SU2 cannot be simultaneously diagonalized. Because if they could, then they would all commute, but they don't all commute. So therefore it's impossible. So, okay, so what does that mean? That means that if you use, instead of using that little tiny circle inside, if you use the other elements now, and you act upon this decomposition, they will not preserve these two subspaces, right? The circle that we picked, this beautiful little circle here, it's going to send this space to itself and this space to itself. It'll send the C to itself and C to itself. But if I use one of the other matrices inside SU2, it will not preserve this. Instead, it will take this guy to this guy, and it will take this guy to this guy. Not that they're guys, they could be, they're unisex, basically, these subspaces. So this is the key. This is the strategy of representation theory, is that you use this beautiful little circle inside to decompose into weight spaces. And then the other people who are interfering, who are not in the pure perfect circle, they are going to move the weight spaces around, and you need to keep track of how they move them around. That's the technique. Okay, so let's see how that works. So to make this work in the best possible way, it's better to consider the complex field. So what we're going to do is take complex linear combinations of everything. So let's take a look. So let's take sigma 1, and let's take sigma 2. And these are, you see, like I want to know how sigma 1 acts on these weight spaces. But the problem is that the way the matrix looks is that it looks complicated because sigma 1, it takes this to this and this to this, but sigma 2 also does the same thing. It takes this to I times this and so on. So it's a little bit confusing. It's easier if I do the following. If I use this 1 and this I to, if I take complex linear combinations so that I kill what's here. So I'll take a sigma 1 plus I sigma 2 over 2 gives me this matrix. Now that looks a lot simpler in this decomposition. So what does this one look like? It looks like the first basis element is killed and the second is sent to the first. So that means that the way that E acts is that it will take this and send it to 0. And it will take this and send it here. It'll just shift it over. That's why this operator is called a raising operator, because with respect to these two weights, okay, anything of weight -1, this matrix is going to take it to something of weight +1. And anything of +1 is going to be sent off the cliff down to 0. Okay, whereas if I take the negative combination, then I'm going to kill this entry and I'm going to get a lower triangular matrix. And this thing is going to do the opposite. It'll be a lowering operator, which takes the space of weight 1 and it will map it to the space of weight -1, right? Because it's either there's either a 1 here or a 1 there, and that will affect, which space is sent to which. And then I'm going to take sigma 3. This is the same as sigma 3. Remember, it was 1 minus 1. So instead of taking sigma 1, sigma 2, and sigma 3, I'm going to take E, F, and H. Okay, this is an alternative basis for SU2, but the problem is the only way that I can make this simplification is if I tensor it with C, which just means that I'm allowed to take these complex linear combinations. Okay, and the Lie bracket is just extended by linearity. So we have a complex linear Lie bracket on this. Okay, so the only reason I'm doing this is because I want this nice formula, this nice format for the basis elements. Okay, so then what we can do is, instead of the commutation relations between sigma 1, 2, and 3, I could figure out what the new commutation relations are. And these are the important relations. Okay, so if I take H and I commutate with E, take the commutator with E, what I get is a multiple of E. HE minus EH. You can see that because E is this, when I multiply by H, I'm either going to pick out +1 or -1, depending on whether I multiply on the left or on the right. Right? And because there's a minus sign, that means that those two signs will contribute to each other, and we'll get 2 times E. By symmetry, we're going to get the same result, but with a minus sign for F. So I'm going to get 2F, minus 2F. And then the bracket between E and F gives H. So this is probably the most used set of equations in representation theory. Okay, what it shows is that the little, if you want a fancy interpretation for this, I would say, if you want a fancy interpretation for this, I would say that the little add action of H on E is -2E, which means that E is an eigenvector for the little adjoint action of H. And F is an eigen, and little f, F is an eigenvector of little add H with eigenvalue -2. And then you have this EF is equal to H. Okay, so why do we need these commutator relations? It's very simple. The reason we need this is because we want to know how the representation behaves in terms of this decomposition. Okay, if we know these commutation relations, we'll know what happens if I apply, different basis elements of the Lie algebra one after the other. How is that going to affect, the decompositions. So let's try to implement this. So okay, so let me go through this part carefully. So if you have the notes, just keep it on this page where you see E, F, and H, and you have the commutator relations, and then I'm going to scroll up here and do this computation. So this is the main calculation, the most important calculation in representation theory is this one. So let's suppose that we have a representation of SU2. That's what I'm going to try to classify. That's what I'm going to try to study. Okay. This means that so we didn't discuss this in detail, but we focused on representations of groups rather than representations of Lie algebra. But in your reading, you saw how they were related. So if you have a representation of a group pi, I'm just giving the example of a unitary representation, then we can take its derivative at the identity element, and that will give a representation of the Lie algebra. And this will be a homomorphism of Lie algebras. What does it mean? It means it's a homomorphism of vector spaces. It's a morphism of vector spaces, a linear map, such that, let me just I think the textbook calls it pi prime, such that pi prime of the Lie bracket of A and B is the commutator of pi prime A, pi prime B. Okay, so the idea is that if we can find a representation like this of the Lie algebra, in other words, if we could take the Lie algebra and represent it by skew adjoint matrices, such that the bracket is sent to the bracket, then what we could do is exponentiate that and get a representation of the group. So that will be our strategy, is that we're going to try to study representations of the Lie algebra and then exponentiate them. Okay, so let's say number one, so we're going to study this representation just like we did here. See here, we took this vector space, which was C2, okay, and we looked at how sigma 3 acts on it, and we noticed that sigma 3 is diagonal, and so this thing breaks up into eigenspaces, and these eigenspaces are the one-dimensional representations, the irreducible representations of that nice little circle. So let's do the same thing. Suppose we have a vector which is in the eigenspace of this operator, rho of H. Sorry, I'm calling it rho now. Let me change. Yeah, rho, sorry. Rho is pi prime, is the derivative of the representation. So it's a representation of the Lie algebra. Okay, so if V is an element which is in the eigenspace of H with weight K. So this is what we call a weight K vector in the representation. So this weight K vector, in the previous example, there was a weight 1 vector, in here, which was 1, 0. And we could see that that this thing, which was H times 1, 0 is equal to 1 times 1, 0. So this is H applied to V is equal to K multiplied by V, where K is equal to 1. So that's what I'm talking about. That whatever the representation is, the question is, where does H get sent? Okay. H gets sent. So this could be any vector space. It could be a high dimensional vector space. This element of SU2 Lie algebra, right? This is going to be represented as a big n by n matrix. That n by n matrix will have vectors of different weights, okay, because it generates one of these U1 actions. Okay, and that U1 action will have potentially many weights. So take any element that has that weight, V, and suppose it has weight K. Okay, then we have this U1 action, which is the exponential of e to the IH acting on V. Actually, I should just to make it more pedantic, more correct, I should write it like this: e to the I rho of H. So this is the matrix that the representation gives for the algebra element H. This could be an n by n matrix. Exponentiate it. This gives me a unitary matrix on V, and that will give a representation of the circle. So now we have SU2, we have this little circle, but the whole thing now is being represented on a much bigger vector space. And that little circle is still acting on that vector space, and we get a decomposition into weight spaces. So we take an element of weight K, and now we apply the raising operator. So if we apply the raising operator, okay, we would like to prove that it actually does what it's supposed to do, that it raises the weight. So how do we prove that? Well, let's apply the raising operator to V, and then let's test what the weight is. So let's apply H to this. Well, the commutation relation says that HE minus EH is 2E. So HE is equal to EH plus 2E. That's using the commutation relation. Okay. And then we use the fact that HV is KV because it is in the K weight space by assumption. And then I get EV, EV, and so I can collapse this, I can combine them, and I get K plus 2 EV. So what this shows is that if V has weight K, then EV has weight K plus 2. So it raises the weight by 2. Okay, this is really simple, but it's the most important calculation in representation theory. It's telling you that you've got in your Lie algebra, you've got fundamentally three different kinds of elements. This one, which generates a U1 and has nice weights and decomposes everything. And then this one, which raises the weights. And this one, which lowers the rates. Let's just do the same computation. If we apply F to V and test it, we're going to get FH minus 2FV. The same computation gives K minus 2. So this is a weight lowering operator. And so I've drawn a picture of it like this. That in general, this is what a representation of SU2 will look like. Here you go. It's almost done here. It's going to be a sum of different weight components for each integer, right? This is Z inside R. Okay, for each integer, I could have some vector space, which is an eigenspace of H. So H sends this part of the space to itself. It's a weight space. So if you look at this, it might look like, for example, there might be, if this is, suppose this is 0, 1, 2, minus 1. Suppose I drew a picture like this. This, okay? So this would be a picture, potentially a picture of a representation, which according to my kind of straightforward notation, there's going to be a one-dimensional weight space of weight minus 3. So that means that the way H acts on it is by multiplication by minus 3. The way that E acts on it is that it's going to raise it over here, okay? And it might be sending it to a vector in here. If I apply F to it, well, maybe it just goes to 0. 0 is it's possible that there is nothing down here. And here, if I draw a double point, like with 2 circles, I usually use that notation to mean that there's a 2-dimensional space of weight minus 2. Okay. Anyway, that's going to be, is that picture clear of basically mechanically how the different parts of the representation act? Of course, the general element in the Lie algebra would be a linear combination of these three matrices, and so you would have to apply a sum of the three results. Okay, so summarize. The summary is that we're going to analyze any representation of SU2 by identifying the weights for a very particular U1 given by this operator. And then we're going to describe how E and F act on the weight spaces. Now let's do that for the standard representation. So with a standard representation of SU2 on C2 has two weight spaces of weights 1 and -1. If I apply the raising operator, it will literally take this basis element to this basis element, right? Because 0, 0, 1, 0, 0 applied to 0, 1 is 1, 0. Okay, so that means that this basis element is going to be sent to this one. And if we apply E again, we'll be sent to 0. Of course, what else could it be? We already have two dimensions here of weights -1 and +1. There can't possibly be anything in the weight 2 because the total dimension is 2. It's C2. Okay, so we've run out. It's no surprise that if we apply E again, we'll get 0. And similarly, F takes this to this. And if we apply F again, we get to 0. Okay, so this picture is a very accurate picture which tells you everything that you need to know about the representation, of the standard representation, the standard representation of SU2. Is that clear? Is that okay? Any questions about this diagram and what it means? So maybe to like completely spell it out, I would say that the diagram, what it means is that this dot, means that we have the point 0, 1. This dot has the point 1, 0. These tell the eigenspaces or weights of H. Okay, and this is the action of E. E sends this to this, and F sends this to this. That's what the diagram means. I just wrote out all of the things that is supposed to be, denoted by the diagram. Okay, so a vector, a non-zero vector in one of these VK weights K subspaces, okay, I'm going to look for a very special one. In our society, we give all the attention, all of the riches and all the attention goes to the top 1%. So the richer you are, the richer you become, and the more rich, and the faster rich, and the acceleration of your rich. The F prime, F double prime, F triple prime. It's all up. It's all up and up for you. Okay, and the one at the top is called the highest weight vector. It's the vector. It's a vector with the highest weight. So in this example, this is a highest weight vector. There's not just one because you can multiply it by any non-zero constant, but there is there is in this case a one-dimensional space of highest weight vectors, and this is a highest weight vector. That's what the definition says. Highest weight vector is one that is killed by the raising operator. So that's like, 1930s style FDR taxes. It's going to get rid of that highest weight vector. 93% or something of that nature. So yeah, so now let's see what we can do. So this is important. It's important, like if you wanted to describe this representation, one way for me to say it is, yeah, this is a really bad analogy because it's going to become very Ayn Randian. So it's going to turn out that in order to know what this representation is, we only need to know the highest weight vector. And as soon as you know the highest weight vector, then you can generate the rest of the representation. Why? Because you can apply the lowering operator. It's trickle down. You know, the top just populates everything in the bottom. Okay. So that's why the highest weight vectors are so important. It's because they can generate the rest of the representation in a certain sense. So let's see how that works. Okay, so let me just see. Okay, very good. So far so good. We're moving right along. Okay, so let's suppose that we have. Okay, so now what I'm doing now is explaining that all you need is a highest weight vector, and you can build a representation. You could just build it by yourself. You don't need me or the book to tell you anything. All you need is these relations. You need to know these relations, right? And you need to know your highest weight vector, and we're going to produce the representation. So let's figure it out. So take a non-zero vector, and let's suppose that it has weight 2. So it's right here, V. And let's suppose that it is a highest weight vector, meaning that E applies to this to give 0. Now we're going to apply F. If we apply F, it will have weight 0. So it will be a vector with eigenvalue 0 for the action of H. Okay. Now the claim is that vector, I'm claiming that when you apply F, it's automatic that it will not be 0. That the vector that you will produce will not be 0. Why? Well, let's take a look. So let's suppose, so if we apply E to this thing that we got, FV, so apply E to it, what's that going to do? That's going to raise it back here. Why am I raising it back? Because I want to see whether that FV might have been 0. So it seems like a weird thing, but this is a good way of proceeding. So EFV is FEV plus HV. That's the commutation relation for E and F. But we know that V is a highest weight vector. So this thing does not contribute because E is acting on it. Okay, this is just product of matrices, basically. So, so if I take this FV and move it up, okay, that will be the same as HV, but HV is 2V, and V was non-zero. So therefore, there's no way that this could be 0. Because if I'm going to take this thing and move it up, do something to it, move it up, and then get something that's non-zero, there's no way it could have been 0. So therefore, it's clear that FV cannot possibly be 0. But it's also clear that it has, well, we already discussed this. It has weight 0 because weight is decreased by the action of F. So there you go. You've produced an extra one-dimensional piece of your representation. You've taken this, you applied F, okay, because a representation should be closed under the action of all these matrices, right? Every time you act by the matrix, you should get something that's in the vector space. And what we did was we applied F, and we got something non-zero, which is of a different weight. And so we grew our representation from size 1 to size 2. And in fact, it wasn't a representation to begin with, because V, in order to be a representation, you have to be closed under the action of E, V, and H. So we're building it, and we're not sure whether we're done yet. So we apply F, and we get an extra piece of the representation. What else could we possibly have? So, well, here, there's another good reason to make this computation, because you might want to say, well, okay, in order to figure out what else is in the representation, I need to take what I have so far, and I need to apply all the matrices to it to see what else I get. And you need to keep doing that until it's finished, right? So you start with V, we produced this, and we checked that these are linearly independent, right? Because they have different eigenvalue for H. So these have got to be independent. So what else have I got? Well, I need to apply all of my operators to these two. Well, if I apply H, I'm just going to get these are eigenvectors. So I'm not going to get more from applying H. So let me apply E. If I apply E to V, that's going to kill. If I apply E to FV, that's going to be 2V, and therefore it will be in the span of these two. So E is not giving me anything more. So what I should do is apply F. So let's apply F again. So we apply F to FV, okay? And I claim that that is also non-zero. So this is, I'm applying F again, and I'm going to get something of weight -2 now. And the claim is that this thing of weight -2 is non-zero. Okay, so why? Well, if I'm going to do the same trick as before. Apply E to this thing, whatever it is. Okay, then what do I get? Well, I use the commutator and I get FE plus H, right? And we already saw that EFV was 2V. So EFV is 2V, and there's an F here. So I'm going to get 2FV, and HFV, well, FV had weight 0. So this term goes away, and I get FV. And so I get 2 times FV, and we already checked that to FV is non-zero. So that means that this thing, FFV, if I apply E to it, I actually get a multiple of FV. So there's no way that thing could have been 0. Okay. So I've got something else. Now my representation has dimension 3, or my potential representation has dimension 3. And so we've got 3 pieces which have weights 2, 0, and -2. And now I make my final claim, which is that I'm done, because if I apply F one more time, then it kills. Okay, and if I apply E, it's not, E is going to kill this, it's going to take this to this, it's going to take this to this. So E doesn't produce me anything more. So the only thing I need to check is that this F kills, and that means that F squared V is the lowest weight vector. You know, they're the Dickensian, you know, people at the bottom of the pole who, you know, are waiting for the dregs from the 1%. And yeah, and you know, F kills them. So why? One way to do this is to verify it just by making a whole bunch of computations. But I'm going to give a better explanation for why this thing is 0. Okay, and the reason is because the weights, they must be a priori symmetric about 0. And why is that? Okay, so in other words, if there's a vector in your representation of weight Q, then there must exist a vector of weight -Q. So why is that? This should have a non-zero here. Okay, the reason is because there's a very nice matrix in SU2, this matrix here. This is a matrix which squares to -1. And so it defines a kind of complex operator. It's something that behaves like the number I squares to -1. This is a matrix that squares to the identity, squares to the minus identity. And the representation will take it to some unitary matrix. And if I look at the conjugation of J on H, okay, what you see is that when you conjugate this matrix, it flips the eigenvalues. So this means that there is a special operator in SU2, which when we act on the Lie algebra, it sends H to -H. Okay. And so that means that if I do a representation, if I have a representation, and if I look at the image of this special element of the group in the representation, okay, then when I conjugate, I'm going to get -pi of H. So this pi of H, this is the matrix this is basically how H acts on the representation. So this will contain all the weights along the diagonal. Okay, and then if I use this invertible matrix as a symmetry, right? This will act on the representation because it's part of the representation. It's a unitary element that acts on the vector space. And if I conjugate, if I change the basis from this to this, then all of my weights gets reversed. Okay, and so that means that there's a symmetry of the representation which preserves the unitary structure. It preserves the representation, okay, but it flips all the weights. Okay, and for that reason, it must be that this thing is the lowest weight because it has weight -2. If I could map it down here to -3, then I could flip the 3 over and I should have something of weight. Oh, sorry, -2 would go to -4, and then I would have something of weight 4, which I don't because I assumed that we had the highest weight at weight 2. Okay, so the weights are always symmetric because of this nice operator that flips the weights.
You could do this exact same argument starting from the lowest weight and working your way up, right?
Yeah, absolutely. Yes, absolutely. There's nothing special about the highest and the low. Unlike our economic system, this thing is totally symmetric. Maybe, maybe we should use it as a model, mathematical model. Just assume, let's say, assume that the income distribution is an SU2 representation, and that the government acts upon it by E and F. And maybe there's a way of maintaining some kind of balance by requiring that it's always a representation, right? There must be something to that.
Just a question.
Yeah.
So we assumed at the start here that we said that V was our highest weight vector, but what we assumed was just that EV was 0.
That's the meaning of highest weight. That's how.
Is there some obvious reason why there can't be another higher, like a weight 4 vector that just E doesn't send V to that, E kills V, but
So okay, the answer to your question is that there could be. However, we are assuming that our representation is irreducible. Okay, and that means that if there were, then we should be able to get to it somehow. And yeah, and so all I'm trying to do here is build an irreducible representation from a highest weight vector. And so that's what I've done. That I started with a highest weight vector. I generated, started here. I generated this, and then this is closed under the action of the 3 elements. And so therefore, it is a representation. Now you could add, after this, you could add another highest weight vector, which is totally orthogonal to this one. And you could build another representation, but then that thing, the result would not be irreducible. So so in general, there could be many highest weight vectors. Each of them would be like orthogonal to the others. Okay, so so the theorem is that every finite dimensional irreducible representation of SU2 is built exactly in this way. This process that I just explained of choosing a highest weight vector and populating down until you get to the bottom will produce all of them. Okay, and so let me draw a picture. So we have this one, which is the trivial representation. It's one-dimensional, weight 0, and raising 0 and lowering 0. So it is just C, where all of the 3 matrices are just acting by 0. This is the Lie algebra, by the way. So here I'm writing rho is the Lie algebra representation. So it's going from SU2 to UN, where this is N. Okay, so this is the one-dimensional trivial representation, and this is the 2-dimensional standard representation, and this is the representation that we just built. It has 3 dimensions, Okay, and we have raising operators and lowering operators. And this is a three-dimensional representation of SU2. And we already saw it. This is the three-dimensional representation, which is a map from SU2. Remember, we saw it to SO3, which is sitting inside U3. So that's this representation. Okay. And then we have one for every single integer, because I could pick a highest weight vector at any one of these points. So this means that there's exactly one irreducible representation for every dimension greater than 0. Okay, and that is extremely different from U1. U1 had Z many representations, and they were all of dimension 1. This has only one representation in every dimension, positive, in every positive dimension. So as long as you know the positive dimension and you know that it's irreducible, the representation is like this. So these, when you look at a diagram like this, what I encourage you to think is that this is an infinitesimal diagram of how SU2 acts on your vector space. You should think that there's a basis of 3 vectors, and that there's an infinitesimal, so there's a basis for the Lie algebra where the way that they infinitesimally are acting is that this one by E is infinitesimally moved in this direction. And this one is infinitesimally moved in this direction, like that, just rotated a bit or shifted a bit. Whereas F goes the opposite way, right? And so you know the infinitesimal action of a basis of the Lie algebra. And then if you want to know the actual matrix action, you can exponentiate those matrices. So you basically would exponentiate this diagram to understand how any element of SU2 would act on your vector space, on your 3-dimensional vector space, on your 4-dimensional vector space, and so on. Okay? And when we say that it's irreducible, okay, that should be obvious from the diagram that no matter where you start, you can get anywhere else by applying the blue and the purple arrows. You do not have an island which is separated from the rest so that you can decompose the representations into 2 pieces that are just sent to themselves. That the entire thing comes as one big chunk, okay? So basically we've seen so far 1, 2, and 3 dimensions, and now we need to see what is in higher dimension. Okay, so is it clear what I'm saying here? Like what the what these kind of. So I've basically given you all of what you need in order to completely pin down the representations of SU2. There's nothing more complicated than what I just said. The entire thing hinges on the commutation relations and on the idea of a highest weight vector, which can be used to generate the rest of your irreducible representation. Okay.
And is this related? Sorry.
Yeah, go ahead.
To earlier when we did the 2 irreducible representations of the matrix, we had like e to the I theta and then e to the negative I theta. So can we set it up in a block matrix using
like this?
Yeah, like can we set it up with a block matrix in the same way using our 3 weights?
Yes, absolutely, yes. So so that's what I did here. So we already saw that there's a representation of SU2 into SO3, which takes this e to the I theta h to e to the minus 2 theta sigma 3, which is basically rotation at twice speed about the z-axis. And that's normally how we would write it. But if you diagonalize this thing, then what you'll see is that you can diagonalize this over the complex numbers. And what you'll get is that this cosine matrix basically has eigenvalues e to the I2 theta and e to the minus I2 theta. And then this is a 1. So what you see is that the three-dimensional representation here, if I use this basis, okay, then the way that H acts is diagonal. It sends this to -2 of itself. This is a -2 eigenspace. This is a +2 eigenspace. This is a 0 eigenspace. And that's exactly what you see here. This is the exponential of so in this case, sorry. -2 sigma 3 is similar to a matrix that looks like 2i. No, sorry. H, yeah. H. So in this representation, tau of H would look like this. It would have weights 2, 0, and -2. And then if you exponentiate this, e to the I theta H, we would get this. So this is the way, this is coming from the diagram. You can read this off directly from the diagram. You just put 2, 0, -2 as the eigen vectors, as the diagonal entries, 2, 0, -2. Okay, and that's the way that the little circle is acting infinitesimally. So you exponentiate that. E to the I theta H would give you this, and that's how the representation acts for the H vector. On the other hand, if you wanted to write E, tau of E, it would have to take the first basis vector to the second to the third. And if we had to write F, we would get the first is sent to 0, the second is sent to the first, and the third is sent to the second. Okay, so this means that these three 3x3 matrices are how the three generators, the three Pauli matrices, it's just that it's different combinations of them. It's a different basis. But that basis is sent to three-dimensional matrices, which act on three-dimensional space. If you exponentiate, you get rotation-like things. It's just that we're using a different basis from the basis sigma 1, sigma 2, sigma 3 that we used before. Okay, so anyway, that's this three-dimensional representation. Okay, so this basically gives you enough information to construct them all. Okay, I just want to give a shortcut to construct all of them all at once. Okay, it turns out that once you know this representation, you can actually construct these from that one. So this is like the germ, the initial seed, which if you apply a certain operation, we will produce all of the others by iteration. And that's a bit unusual. Normally you can't do that for general groups. So the strategy is that we're going to build them from the standard representation. And the way we do it is by using a certain functor, which is called the symmetric tensor product. Okay, so that's a very easy idea. If you have a vector space, you can take the tensor product with itself. And inside there, you have the symmetric elements. And those are the elements like this. So this is not a symmetric element because if I switch the two, it's going to be different. But if I switch the two in each of the summands, then I'm going to get the same sum, right? The switch of this is going to be this, and the switch of this is going to be that. So in total, this vector is a symmetric vector in the double tensor product. Is it clear what the basic idea is? You want to consider expressions, tensor products, two tensors, but you want them to be actually symmetric under flipping the two factors. So if I have a basis for V, then what is the basis of Sim2V? Well, here's a basis. I can have E1 tensor E1, E2 tensor E2, E3 tensor E3, En tensor En. Those are all symmetric. Okay, but if I also take two of them, EI and EJ, which are different, then I can take EI EJ plus EJ EI. And here I'm just making it linearly independent from the previous elements on the list by letting I be less than J. So that means that I have N of these, and I have N choose 2 of these, and the sum is Nn plus 1 over 2. That is the dimension of the second symmetric power of V. Okay. So, and then if I do the same thing inside V tensor V, I have the triple symmetric ones. So those are the ones that if I take the 3 elements and if I permute them in any possible way, I get the same result. So they're completely symmetric in all 3 entries. And you have to take, sums of elements that are symmetric as a sum. The individual summands do not have to be symmetric. It's only the sum that has to be symmetric. And okay, so this is nice and all that, but there's a very fast way of understanding these symmetric tensors. We can just use our favorite symmetric things around. Symmetric things are just polynomials, because you know that x times y is equal to y times x as a polynomial. So an expression in polynomials is automatically symmetric in a sense. So this is how we'll do it. So if you take, instead of thinking of this basis of V, identify this basis with polynomial, with the polynomial variables x1 up to xn. Okay, and if you have a polynomial which has homogeneous degree d, that's going to look like this, like x1 squared x2 plus x3 squared x4, right, plus x5 cubed plus x1 x2 x3. This is a homogeneous polynomial of degree 3. Okay, and my claim is that it is obviously symmetric in the sense that polynomials are already symmetric. You don't have to force them to be. This is equal to x2 times x1 squared. Okay, and so if you want, you could identify this with the symmetrization of x1 tensor x2. So what you could do is you could say that what this really means is that you should take x1 tensor x2 plus all of its permutations, just to force it to be symmetric. And then the polynomial that you assign to that is just this one. So this is a way of labeling symmetric tensors by polynomials. And that labeling is a one-to-one labeling. Okay, so symmetric tensors are in one-to-one correspondence with polynomials. Symmetric p-tensors are polynomials of degree p, homogeneous polynomials of degree p. Sorry, I just wrote what I just wrote up here. Homogeneous polynomials of degree d is the same as the dth symmetric power of this vector space. Another way of writing it in a fancy way is that if V is the span of these elements, then the sum, the infinite sum of dth symmetric powers is the polynomial ring. Okay. Now, all of this is very general. In the special case where V is C2, this will do wonders, because if you look at C2, so if you look at C2, let's say it's the span of X and Y. And if you look at Sim 2 C2, this is going to be the span of X squared, XY, and Y squared. 3-dimensional. This is 2-dimensional. If I do Sim 3 C2, this is going to be X cubed, X squared, Y, X cubed, Y, X, Y squared, and y cubed. This is 4D. Okay, so this is the really cool thing, is that if you know how your representation works on here, that means you know how it acts on x and y. And if you know how it acts on x and y, you can just let it act on polynomials in x and y. And in this way, you produce all of the irreducible representations of SU2 just by taking higher and higher homogeneous degree. So let's see what extra data I want to give here. You see here, if I have a tensor product, then I can act by any unitary matrix in SU2 by just acting on the two factors at the same time. Okay, so when we tensor a representation with itself, it's also going to be a representation. And when we take the symmetric tensor powers of a representation, that will also be, as you can see here, a representation. You just let U act on each of the things in there. Okay, and so therefore, any vector space, which is a representation of a group, the symmetric powers will automatically be a representation. Okay, and so then the question becomes, okay, fine. If you take C2 with the standard representation of SU2, and you take the symmetric Hudith power, which representation do you get? We classified them earlier. So we need to draw the diagram of this homogeneous polynomials representation. And we can easily see this. So so if V is this one, this is the standard representation. So it's the same diagram as before. What happens if we take the symmetric square? The symmetric square will have E minus, E minus, E minus, E plus, plus E plus, plus E minus, and E plus, E plus. These are the three generators for the symmetric square. And how do we check this? Well, how do we determine, which representation it is and the fact that it's irreducible? What we need to do is look for highest weight vectors. If we could find a highest weight vector, then we already know this thing is a representation. So that means that we can populate the rest. We can see whether the dimension is the right dimension and see whether we got the complete description of the representation. So we're looking for eigenvectors for the action of the Lie algebra. Okay, and here we have just one confusing thing which you have to think about, and that is that it makes a big difference whether you're acting by a group element or a Lie algebra element. If you act by a group element on a tensor product, you should act on both simultaneously. But if you act by a Lie algebra element, what you're really doing is you're differentiating the group action. And when you differentiate this with respect to a path of these matrices, you're going to have two terms, whether you differentiate this term or that term. So when you act by the Lie algebra, it does not act simultaneously on both factors. It acts by a Leibniz rule, where it acts on the first and does nothing to the second, plus doing nothing to the first and acting on the second. Okay, so when we are looking for an eigenvector in this representation for the action of H, the action is really this one. Okay, so for example, well, what would you guess? If you knew that E plus was the highest weight vector for V, what would you guess is the highest weight vector for Sim2V? Maybe it's not so surprising that it would be E plus tensor E plus. Okay, that would be very high in weight. And indeed, if we apply H to E plus tensor E plus, we're going to get HE plus tensor E plus E plus tensor HE plus. HE plus, we already know what it is. It's 2 times E plus, and this is 2. So we get 2. Why did I put 4? H times E plus. Oh, it has weight 1. I'm sorry. I should have highlighted that before. HE plus is weight 1. And so I get 2, right? And so what this means is that this vector, which we're guessing is the highest weight vector, has weight 2. And therefore, if we look at our list, we see that there's only one representation that has highest weight vector with weight 2. It must be this representation. The only thing we need to check is that it is actually a highest weight vector. So let's apply E to it. You apply E to it, we get E times E plus, that's 0, plus E plus tensor E times E plus, that's 0 as well. So it's killed. Therefore, it's a highest weight vector. So we found a highest weight vector with weight 2. Therefore, it must be the irreducible representation with highest weight 2, just because there's no other thing it could be. It has that dimension. It has the same highest weight vector. It has the same diagram, has the same action of the Lie algebra. So doing exactly this argument proves that this SDC2 is the D plus 1 dimensional irreducible representation of SU2. That's it. That's how you classify them. That's how you build them all as symmetric powers. And so, yeah, you can build other representations. Now, the problem is that if you take 2 of these representations, let's say you take something weight minus 1, 1, and you take its product, let's say V and V, minus 1, 1. If you take V tensor V, not the symmetric tensor, but just the tensor, right? Then you're going to have E minus tensor E minus. You're going to have E plus tensor E plus inside this vector space. You're going to have E minus tensor E plus, and you're going to have E plus tensor E minus. So it's going to be a 4-dimensional space. Okay, but the problem is that this one will not be irreducible because we know that inside here there's S2V, Sim2V. And this has dimension 3. Okay, so, and we know that these representations, it always decomposes into irreducible representations. So what we know is that it must be that V, tensor V, is a sum of this representation, the 3-dimensional representation, plus the 1-dimensional representation. Okay, and the way physicists write this is that they use bold letters. It's a terrible notation. They use bold letters and they write 4, oh, this is too bold. They write 4 is equal to 3 plus 1. Okay, and this, by this they mean that the unique 4-dimensional representation of SU2 is a decomposition of the unique 3-dimensional one and the unique 1-dimensional one. But the question remains, what is this 1-dimensional one in here? Like, what is it? So you should think about that. Where inside this 4-dimensional space is there a 1-dimensional space, okay, that is an irreducible representation just by itself? And guess what? It's easy to find because it has to have weight 0 under this special circle action inside it. So what you're looking for is something of weight 0. So basically, the idea is that you could graph this representation, and the way you would graph it is this way. You would say there is an irreducible representation of size 3, and then there's another one on top of it, which is contributing at 0. So it's really the sum of 2 irreducible representations, which overlap exactly here. Okay, and so this is why you see these diagrams, these weight space diagrams for representations. And it's a very nice theory. We're going to do it next week for how to decompose representations of SU2 when you take their tensor product. Because of course, you know, if we have if we have like 2 qubits or 5 qubits, we're going to take the tensor product of all 5 of them, right? And then we might want to see how a certain SU2 acts on the entire quantum system. We have to decompose it into subsystems, which are summing together to the full thing. Okay. I'll take some questions, but sorry for going over.
So when we find the irreducible representation, so the matrix we get would be if we diagonalized the representation.
The which representation?
So if we were to diagonalize the representation, then
Yes.
the diagonal element would be the irreducible ones on the.
No, so be careful. So you see, when we draw this diagram, okay, so let me just grab one of these and let me put it over there. Let me just try to boil this down to the most practical level. Okay, so when you see this diagram, okay, this diagram needs to be interpreted in the following setting. Okay, that SU2 tensor C is spanned by H, E, and F, where HE is 2E, HF is 2F, minus 2F, and EF is H. Okay, so that's number one. You need to know that, first of all. Number two, representation means that we need a Lie algebra map. We're going to take a map to see n by n matrices. Okay, so that means that in order to define a representation, I need to tell you where is H sent, where is E sent, and where is F sent. They will all be sent to n by n matrices, and that will define, from a Lie algebra point of view, it will define the representation. So this is a representation of the Lie algebra, and then this leads by exponentiation to a representation of SU2. Okay, so, and the diagram is telling you literally where H, E, and F is going. So that means that we're going to take, so in the diagram above, I have these 4 red dots. That's going to be C plus C plus C plus C. This is my vector space. And you can see that it has been decomposed. Now, if it's being decomposed, I'm in big trouble because I'm supposed to be classifying irreducible representations. Okay, and irreducible representations do not decompose. So what is this decomposition? It is a decomposition for the little truck driver, the little circle inside the group. It will decompose the vector space in this way. So that means that, and the truck driver is H, the Hamiltonian always drives the system. And so the eigenvalues will be -3, -1, 1, and 3. That is H. Okay. Then what is E? Well, what is E doing? E is moving to the right. So that means that it's got to take the first basis element to the second to the third, and the third to the fourth. And F does the opposite. Okay, so that's it. That is exactly how you interpret this construction. That's all you need to know. The whole representation is given. Now, the thing that is slightly annoying, but it's actually part of the clever aspect of this, is the fact that we're using E, which is, it's a sum. It's like sigma 2 plus I sigma 3 over 2, something like that, right? So instead of using the Pauli matrices, which are the self-adjoint observables, we're using weird complex linear combinations of them, which are not physical in the quantum mechanics. So these here, these are self-adjoint, but E is not. It's not an observable. So this is a mathematical method for classifying the representations. But actually, it turns out that the mathematical method was invented by physicists anyway. They were called raising and lowering operators. They're non-unitary, they're useful anytime you study these representations. So it's not surprising they were discovered long ago. Does that help?
Yeah, thank you.
You're welcome. Okay. Have a good weekend, everyone.
Can I ask one thing?
Yes, yeah. You always ask at the very last moment.
I'm sorry.
I don't know why you do that. Okay, yeah, go
I'm
ahead.
torturing you.
No, it's fine.
So like you just said, right, the physicists call these raising and lowering operators. So when you're studying like the harmonic oscillator or something, you you construct like these raising or lowering operators that give you the different eigenstates. Could you make that connection like explicit between these representations and those?
Yeah, it's very closely
cases?
related to that. Yeah, they are the same operators. The funny thing is that they have a slightly different role in that case. Yeah, we'll definitely see more. We'll definitely see more about that. Yeah, we'll see more about that. It's a slightly different phenomenon. But the reason for that is because of a symmetry that the harmonic oscillator has. So, it's rather that yeah, I'll try to comment on it then when we do it. Then you'll see exactly why they're the same. And when we talk about the Fock space as well, the Fock space is really where you really see this raising and lowering operator, and you start to see that this is exactly how Dirac was considering the Dirac C, like this. He was considering that that you have infinitely many weights in positive and negative degree, and so the idea was that if you have an electron, the meaning of that is that you just have one extra state beyond this sea of electrons, and that was raising just one state. Yeah, we'll see. I'll postpone discussion till then, but you have the right idea.
Thank you. Have a good weekend.
See you later.